Okay, for what we have in the crossover going from just eigenvalues to eigenspaces, now we have lambda is going to be eigenvalue of a square or n by n matrix A if and only if the equation A minus lambda I quantity times x is equal to 0 has a non-trivial solution. I mean non-trivial as in at least one free variable. And we have the set of all solutions, okay, from this equation is just going to be the null space of the matrix A minus lambda I. And this set is going to be a subspace of Rn and is going to be what is referred to as the eigenspace of A. That corresponds to the eigenvalue lambda. And it says that the eigenspace consists of the zero vector and all the eigenvectors that correspond to lambda. And now in looking for eigenspaces, okay, and we have just as an example, it says to find a basis for the eigenspace corresponding to each listed eigenvalue. Okay, and say we have a matrix A that is a 3 by 3, and we have the top row to consist of 3, 0, 1. Second row we have 53, 2, and 1, and the last row we have just the number 1 running across. And we'll say that for the eigenvalue listed, we'll just say that is equal to 6. And so we have in the setup for the case of what we have for A minus lambda I, okay, and with lambda at 6, we have A minus 6I. So we're looking at the difference between A and 6 times I, and for what we have in 3 by 3 matrix terms, the difference will end up as negative 3, 0, 1, 53, negative 4, 1, and 1, 1, negative 5. And with the difference set up, okay, we can take that times x and set equal to 0. And if we take what we have and write as an augmented matrix, okay, so going from the 3 by 3 from A minus 6I to a 3 by 4, again, having 0 as the fourth column, and again just writing what we have as an augmented matrix. And if I were to reduce, I'm just going to go ahead and write down what the reduced echelon form is going to be. And here we have 1, 0, negative 1/3, 0, 0, 1, negative 14/3, and 0. And here with zeros running across. Okay, now this will signify that x of 3 is going to be a free variable. And so we have, just for the general solution, from the top row, we have x of 1 is going to be 1/3 of x of 3. X of 2 is going to be 14/3 of x of 3. And again, we have x of 3 is going to be a free variable. And so we have just for the solution in x, we have x of 3 times, and we have the vector 1/3, 14/3, and 1. And what we have here with the 1/3, 14/3, and 1, we can say this would be the basis or a basis for the eigenspace. Okay, so we have a basis. We have the set consists of 1/3, 14/3, and 1. But let's say that if you want to rewrite this in terms of non-fractions, what you can do is that considering that we have the eigenvalue to be at 6, you can multiply the set by 6. So if you're to multiply 1/3, 14/3, and 1 by 6, another basis could be like 2, 28, and 6. Or if you're to go even higher, if I were to multiply by 6 again, I could have like 12, 168, and 36. So you have like these among possibilities as a basis for the eigenspace. And another situation where we can look for a basis for eigenspace, and we can say that we have A to consist of 6, 4, 7, 3, 7, 7, 3, 4, 10, and we can say that we have the eigenvalue will be at 3. And if I set up the foundation with A minus lambda I, okay, we're going to have the same values along each row with 3, 4, 7, 3, 4, 7, and 3, 4, 7. And setting this up times x and setting equal to 0. And so what we're going to end up with here is that since we have identical elements along all the columns, we're going to have, if you were to reduce all the way to reduce echelon form, Okay, it's going to turn out that both x of 2 and x of 3 will end up as free variables. And we have the reduction be 1, 4/3, 7/3, 0 at the top. And we have the middle and bottom row to consist of 0 alone. And so we have just with our solutions, okay, again, x of 2 and x of 3 are free variables. And we have, however, for x of 1, okay, we have equal to negative 4/3 of x of 2 minus 7/3 of x of 3. And just for what we have for x, we have x of 2 times negative 4/3, 1, 0, and we have plus x of 3 times negative 7/3, 0, and 1. And a basis for eigenspace, we can have our set of the two vectors that we have involved, okay, concerning respectively for x of 2 and x of 3. So we can say we have negative 4/3, 1, 0, as well as negative 7/3, 0, and 1. And again, if you do not care for the fractions, you can consider that we had the eigenvalue to be at 3. So if I were to multiply all the elements in the set by 3, you can have like another possible basis for eigenspace, like at negative 4, 3, 0, negative 7, 0, 3. Another possibility, say if you were to multiply by 3, could say something like negative 12, 9, 0, along with negative 21, 0, and 9.